In this video, I'm going to show you the process that I use to extract a time constant from the exponential approach to equilibrium that we get with a high-pass or a low-pass filter, a first-order high-pass or low-pass filter. So I'm going to be using my own Python sort of plotting environment, but you can do the same thing with MATLAB or Matplotlib, whatever you like. But I'm going to bring up my plotting environment in a terminal, and I'm going to make a figure and configure the font size. It's a little bit bigger. And make this a little bit bigger so we can see it. And now I'm going to load some step responses that I have that are saved as a comma-separated variables file. So I've got a low-pass step response. And just to show you what that looks like, we can plot T1, T2, channel 1, channel 2, and I'm going to do this just with lines and no dots. And you can see here in blue I have the input step. It's going from roughly 1 volt to 4 volts, and you can see I have here in green the low-pass filter. It's just an RC circuit that's making a low-pass filter. The R is 15.8K, and the capacitor is 10 nanofarads. And so the time constant that we would expect, 15.8K times 10 nanofarads, would be, looks like 158 microseconds nominally. Okay? And so rather than doing the usual thing of trying to look for where the green curve gets to within 1 minus 1 over e of the final value, I prefer to actually use linear regression and take advantage of the fact that we can fit a straight line to the log of the voltage versus time, and use a bunch of points for getting a nice average value of the slope, and from the slope we can get a read on the time constant. So how do I do that? So the basic idea here I could illustrate by plotting T2 comma channel 2 minus the min of channel 2. So this is not approaching 0, it's approaching something a little bit less than 1 volt, but if we subtract off the minimum value, we'll translate that curve down so it's exponentially approaching 0. And let's put this in, let's see, blue dots, blue line, so we can actually see the data points. And here I can just make it a semi-log plot. And what I can do in here is zoom in. And you can see that this is a pretty decent straight line on a semi-log scale here, down till we get to below the resolution of the instrument that I was using to measure the output waveform here. And so over this nice, roughly 2-decade span, it's a nice straight line. And so we should be able to fit a straight line to this data, or this curve, and get a nice read on what is the slope of this exponential curve. And so the way that I'm going to do that is I'm going to use a function which I wrote called line fit. And this is a Python implementation of line fit, but I also have a MATLAB implementation, and I will put a link to the a GitHub repository where you can get the MATLAB version of this function. But the basic idea is we pass it an x, a vector of x values and a vector of y values. And we pass it a little numerical parameter called epsilon, and this is an optional argument with a default value of 0.001. And the basic idea is it scans through these XY pairs, and it tries to find a run of continuous data points, or contiguous data points, that fit a straight line to within 1 minus epsilon, to within an r squared value of 1 minus epsilon. And it basically returns the first index that it used, the last index that it used, and the slope, the intercept, and the number of points that it used in the fit. Typical range for epsilon is somewhere between 5 times 10 to the minus 4 and 5 times 10 to the minus 3, and the default value is basically 1 times 10 to the minus 3. You can obviously use a different linear regression tool for this. That's fine. What I got fed up with trying to slice out the part of the curve that I wanted to fit, and I came up with this way of automatically trying to find it. So it basically tries to find a range of points that are at least 10 points that are right next to each other that fit a straight line to within this tolerance value, and that has a steepest slope. That's the basic rubric that the function tries to use to fit the straight line. And so what we're going to do is we're going to say first, last, m, and this is going to be down because it's the down going one, b down, and n is equal to line fit x, and then we're going to, or t2 rather, that's the x values, and then we're going to do log of channel 2 minus the min of channel 2. So we're passing in the log of the shifted down channel 2, and I'm going to use the default value, which is 1e minus 3. I'm going to put it in there just for the sake of putting it in there. And you can see it complains about division by 0 at some point because one of these points is 0 because we subtracted off one of the values and that one became 0. And taking the log of 0 gives you not a number. And so it complained about that, but apparently since it used 61 points in the fit, it did find something. And so what we're going to do is we're going to plot T2, and then we're going to plot channel 2, and we're going to plot the fit, exp of m down times T2 plus b down, and then we're going to shift it back up, min channel 2, and we're going to put the original data in a line style of blue dots and blue lines, and we're going to put the fit in line style of a solid black line. And of course, the exponential gets way, way big, and so we're going to use y limits 0, 5 to zoom in, and you can see that we've got a very nice fit here to this particular part of the curve. And I'm going to also show you how it would fit the upgoing part of the curve. So the basic idea here is we can do the same thing first, last, m up, and then b up, and T2. And now what we're going to do is pass it the log of the max of channel 2 minus channel 2. And what this does is it basically flips the curve upside down, so the upgoing part of the step response is actually now downgoing, and it's shifted it down so that it's approaching 0 from above. And so when we do that, and I'll again use 1e minus 3 for that, we don't get any complaints at that point. And let's see, we got, again, about 60 points or so involved in the fit. And so what we can do is add that to our plot here. So the third thing we're going to plot is the max of channel 2 minus exp of m up times T2 plus b up. We're going to add a style for that third curve, and we're going to make that also black lines. And now we've got the same kind of deal, only from the other side. So we're going to zoom in to 0 to 5, and you can see that we've got actually quite a nice fit here. And so we're using all of these points to constrain our estimate of the time constant. So, what would the time constant be? So M up is the slope we got from the upgoing fit, and M down is the slope we got from the downgoing fit. And you can see they're both around, 6,200, minus 6,200. The slope of the exponential should be minus 1 over tau. And so we should be able to back out tau from minus 1 over the slope. So this upgoing slope would give us 160.3 microseconds, and the downgoing fit would give us 161.3 microseconds. And so the nominal tau, we said, was 158 microseconds, and that's not too far off. So the extracted slopes that we get from this linear regression fit from the to the log of the data versus time is pretty close to the expected value. And it's probably actually quite good because the especially the tolerance on the capacitance is plus or minus 5% or plus or minus 10%. And so I think if we were to figure out what is the deviation between the expected 158 microseconds and 161.3, we would find that that probably fits within the plus or minus 5% tolerance of the capacitor quite nicely. So I also have a high-pass filter step response. So if I load CSV, high-pass step.csv, can see how I would use this technique in that context. So if we plot channel 1 and channel 2, you can see here in blue we have the same step that goes from 1 to 4 roughly, but here we have an RC high pass filter, and so we see the fast upgoing edge couple through, but it returns to 0, and then we have the fast downgoing edge couple through, and it goes back up to 0. And then it goes up and down and stuff like that. So it's not returning exactly to 0. So if I turn the grid on here, you can see it's biased up slightly to positive values. Okay, and so what I'm basically going to do to make it approach 0 is to subtract off the mean value of the green curve. And I'm going to take the absolute value so that all of these spikes are approaching 0 from above. And we're going to use the same basic idea. So we're going to do first, last, M high pass, B high pass, N equals line fit, and we're going to pass it T2, and we're going to pass it the log of the absolute value of channel 2 minus the mean of channel 2. Close the apps, close the log. We're going to use 1e minus 3 again. And we're going to see we got 66 points involved in the fit in this case. And so what we're going to do is plot T2, channel 2, and then we're going to do, it's either going to be plus or minus depending on whether it was one of the upgoing step responses or one of the downgoing step responses that it latched onto, but let's assume that it's the downgoing one to begin with here. So we're going to do exp of B high pass, rather M high pass, times T2 plus B high pass, and then we're going to do plus the mean of channel 2 compensate for the offset that we subtracted out. And then we're going to do, again, let's say blue dots, blue lines, and black lines for the fit. And let's do, in this case, we'll zoom in from minus 3.5 to 3.5. And it looks like we got the wrong sign here, so we'll just flip the sign. Change the limits, and you can see here, if I zoom in, that we've got quite a nice fit. this particular response to the downgoing part of a step. And so the M high pass is, in this case, minus 6,500, and so the time constant we would get is minus 1 over M high pass, and here it's 153.7 microseconds, which is, again, probably within the plus or minus 5% of the nominal value that we would expect. Anyway, so that's how, that's just a quick tutorial on how I would go about extracting the time constant from a step response and not bothering with this kind of how much time does it take to get within 1 minus 1 over e of the final value using some kind of data cursors or something like that. If you've got linear regression and you can very easily average over a bunch of data points, like 60 data points, why not do it? You're going to get a better read on it. And so that's it for this. Hope it was useful, and thanks for watching.